everybody. Good to see everyone again this morning. It's amazing to be here. We actually had a bunch of little last-minute registrations, so we're closer to 13,000 people here, which is amazing, so thank you for that. Today's kind of theme for KubeCon is going to be very much focused on end users. This job, I have a fun position in talking to a lot of organizations out there that are adopting cloud-native technology in all different phases, from like early days to massive deployments. And you know, I thought this time around, how fun could it be to kind of do maybe a set of like quick little lightning talks from companies from different industries and so on, to talk a little bit about their adoption of Kubernetes and other CNCF projects. So to kind of kick off this fun parade of people to talk about their cloud-native adoption, I'm gonna go kick it off with a person, Stephen from HSBC, to talk a little bit about what they are doing. So let's get this thing started. So let's get Stephen on the stage here.
Thank you.
You made it. Good luck.
Good morning, everyone. HSBC embarked on our Kubernetes journey back in 2018. And since then, we've now running hundreds of clusters, supporting workloads for markets in the UK, China, Hong Kong, Mexico, and many others, as well as our retail, wholesale, and institutional business, running on premises and in the major hyperscalers. Today, I want to talk about the retail bank's microservices API solution, the service hosting platform. This started life as an experiment in the public cloud adoption team to see if our existing on-premises platform could be migrated to cloud. And by 2019, our first 3 clusters were hosting live workloads, and we were ready to start on our migration project. We're currently servicing around 600 million discrete hits a day to our platform, which is running at the moment 7,000 production services, with many more still to migrate from our legacy platform, all running across only a dozen or so clusters. As you can see, we scaled up very quickly, and we soon encountered the sorts of problems that you don't see in smaller clusters. Rather than waiting to become a victim of our own success, we had to shard our workloads based across individual markets, an approach that also helps us to manage our blast radius along business lines. Our clusters are very stable, thankfully, but change can still be a bit of a pain problem. So to mitigate these issues during upgrades, we run our clusters in a blue-green configuration, rehydrating the new cluster from backups and only cutting over when we're confident that the new cluster is stable. At the scale we operate at, cost is also a huge challenge. And we've had to develop ways of holding teams accountable for their spending, giving them the tools they need to manage the financial footprint of each workload. Responsibility is shared, so it's our responsibility as a platform to make sure the core service is optimized. And the onus, however, remains with the tenant to keep a tight rein on costs by provisioning elastically, based on demand, and only using what they need. The industry trend at the moment is very much towards a more democratic and devolved tenancy model, with smaller clusters allowing engineering teams the flexibility that they demand. In our case, however, we work in a highly regulated organization with hundreds of IT controls that we need to satisfy. But with a high degree of consistency across our workloads that we support, a more centralized model still makes sense for us. Our product roadmap is ambitious, and it takes us several years out into the future. We're looking at availability and resilience, because even in commodity clouds, we can experience failure. We plan to move to a hot cluster model, which means storing our reference data from etcd outside of the cluster and adopting a more declarative GitOps-based model. We're also looking at adopting ambient mode Istio, with the help of our partners from Solo.io, with a view to saving maybe hundreds of thousands of dollars off our annual cloud bill. And we're looking at improving our shared responsibility model, providing better guardrails for our tenants so that doing the right thing becomes easy, and that the security and availability of our workloads becomes even easier to test, optimize, and maintain. With all this growth, it's unsurprising that I am hiring, and we have jobs open in our China and India tech centers in Guangzhou and Pune. So if you're interested in working at a scale that few other organizations operate at, you can get in touch with me on LinkedIn. I'd be really happy to hear from you. And finally, I just want to say a huge thank you to Chris and the team at CNCF for the opportunity to talk to you this morning. And I wish you all the very best for KubeCon 2025 here in London. Thank you.
morning, everyone. I am Carlo Fisicaro, Chief Technology Officer at PEPTONE, and this is Fabio Roddi, our Head of Engineering. PEPTONE is a biotech company based in Switzerland, and the click is not working. Anyways, I'll keep going. In the meantime, if you want to try, we are focused on drugging what are called disorder proteins. Disorder proteins are a very peculiar class of proteins that can be described by standard experimental techniques. And in particular, okay, I think they're trying to restart it. It's a very exciting field, by the way, and today I'll try to explain you why we at PEPTONE focused on these proteins. In the meantime, these proteins are involved in a mass majority of cancers, and they're involved in many neurodegenerative diseases. So they are kind of important for the whole mankind. And I think we can move on. Main experimental techniques fail at describing those proteins. I don't think this is showing up, isn't it?
It's okay, let's just...
I'll just get going. We created at PEPTONE an experimental technique for the first time able to resolve the dynamics of those proteins. And we managed to do that with a super high resolution technique we call hydrogen deuterium exchange mass spectrometry. And we managed to get the highest throughput in the field. When it is showing up, please tell me.
I'll let you know.
Okay, I think it's going now. Look at this example. We generated with a text-to-video experiment here, model, this video. So an avocado sitting on an armchair. And as you can see, the avocado here is empty. Hopefully you can see that. Okay, you can't. It's a very cool video, by the way. Thank you all. I promise you, when it will go up, it will be super cool to see. Anyways, we created a new model, a new foundational model, to generate what is called an ensemble of those proteins. I'll walk in the meantime so that we make it more engaging. So these ensembles are what the pharma field is lacking nowadays, and this is something we are focused on. It's like looking at a video. You can appreciate all the details you have in a video only if you see the whole video, not just a single frame. This is the same for proteins. We look at the video, we simulate the ensemble. And we do that with this foundational model I'd like to talk about, we'll see later. And everything has been trained on DGX Cloud, so in partnership with the MIT, PEPTONE, University of Copenhagen, and NVIDIA DGX Cloud. And we call this model PEPTONE. It will be out, it will be open source, everyone will be able to use it. Fabio, it's not...
Yeah, okay. It's a nice toy. Anyway, we're building, as Carlo said, we are building our model on Kubernetes. We have distributed training in mind for the get-go, partly because obviously it's going to become a pretty big model and it won't be able to fit on a single GPU, partly because we want to accelerate the development cycle. We chose DGX Cloud from NVIDIA as our Kubernetes provider. They provide a very nice platform with high-performance networking, storage, distributed storage, and game scheduling, which obviously you need for these kind of things. And for us, it was really easy to move from our smaller development environment to a big full-feature cluster. Basically, just meant putting our training script in a Docker container, running it as a distributed PyTorch training on the cluster, and then just kick back, take a
Thank you, Fabio. I think it is showing up, so I'll wrap it up real quick.
Okay, just show the avocado video.
So I go to the avocado, indeed, because this is kind of cool. As I said, this is a text-to-video model. We have this prompt, an avocado sitting on an armchair. You see, the core is empty. This is something you would not understand looking only at the first frame, right? We at PEPTONE developed a technology to do the same with proteins, generating what is called an ensemble, starting from an amino acid sequence. And here's the thing, if you think about it, you don't really care if a pixel in an image is misplaced, right? Well, with proteins, it's not like that. A single atom misplaced will push the energy to infinity, making the ensemble useless. That's why we needed to change the neural architecture under the hood and come up with a completely new ensemble evaluation metric. And before thinking about any kind of AI-driven process, we need to see those states, the red ones, and we need to see them experimentally. And we need to see them for a protein alone in solution and the presence of a drug. There is a technique for doing that. It's called hydrogen-deuterium exchange mass spectrometry. And it doesn't work for these other proteins. That's what you see here. Everything is red. It means we don't have enough resolution. Well, we at PEPTONE created a new protocol to get ultra-high resolution and much superior throughput. And we use this data set to create we use this technique to create a data set to train PEPTONE, our ensemble generator.
Yeah, I mean, we can already went to this stuff, but as I mentioned, we run our training on Kubernetes. And, well, actually, also the entire stack that does the analysis for the mass spectrometers runs on Kubernetes as well. But I think we can skip over this.
Thank you, Fabio. And everything runs on Run AI. So, in partnership with, as I said, MIT, University of Copenhagen, and NVIDIA DGX Cloud, we created this model. This is a state-of-the-art model. Ladies and gentlemen, this is how we make drugs, and we are PEPTONE. Thank you.
Thank you.
Hi, my name's Tyson Singer. I'm very much hoping for fewer technical issues than the last folks. And I see we're making progress. Bear with me. At least I got through the part of what's my name successfully without the slides. I'm the VP of Technology at Platform. And here are our slides. Fantastic. So before I get started, first, I want to do a big happy birthday shout out to Backstage. Spotify, thank you. Spotify open sourced the framework for our homegrown developer portal 5 years ago in March of 2020. And the project took off from day one, and it has accelerated from there. Over 3,000 companies have adopted Backstage to build their internal developer platform, or IDP. Within Spotify, it's used by over 700 R&D squads every day to help us ship and maintain our products. Before we open sourced Backstage, we'd already been using it for quite a few years. And it was helping us solve a whole range of developer experience problems and issues: context switching, fragmentation, cognitive load, things you're all familiar with. It had become invaluable to us. And so we went ahead and open sourced it. We thought that other companies would find it valuable too. But we also had another motive. It wasn't just about sharing. Our ambition from the very start was for Backstage to become the standard for IDPs. And now I have found the first technical issue. My slides are not showing up correctly from the perspective of the speaker notes. We'll see if the folks in the back can help me out here. If we can get the fonts changed a little bit, that'd be amazing. There we go. Fantastic. So, great. We've open sourced Backstage. That sounds great. We've got other people using it. But sometimes you have to be careful about what you wish for. Now we were no longer building for ourselves, but we're also building for everyone else. And at times, those things really did feel like they were competing with each other. So I'm going to give you an example. We had to rewrite our entire back-end system. And that was not on our roadmap. But we saw that adopters really needed an easier way to build and integrate plugins. So we did the work, building with the community and rewriting the whole Backstage backend over the course of a year. And when we launched it, not surprisingly, it was great for everyone. Everything about the new Backstage backend is simpler to work with, and that applies to us as well. And so now we're in the middle of completely rewriting the front end. So there's been this tension in how we balance internal priorities with external ones. But ultimately, we believe it's a virtuous cycle. If we hadn't open sourced Backstage, we'd likely still be living with our previous, more complicated backend system. So in 5 years, we've gone basically from this very thin framework for building an IDP to a better Backstage than we could have built on our own. And so now we've taken that one step further to create the best IDP for the future. Spotify Portal, our SaaS product built on top of the OSS Backstage. All of which proves out our original idea. Investing in the community has been an investment in ourselves as well. And because of that, we expect an even brighter future for Backstage ahead. So I want to thank everyone else who's been an end user and a contributor to Backstage. Thanks.
Hello, everyone, and welcome to KubeCon and Cloud Native Con London. My name is Katie Gamanji, and I am a senior engineer at Apple. I'm also part of the TOC, or Technical Oversight Committee, within CNCF. Last year at WWDC, we introduced Apple Intelligence, a personalized intelligence system that brings powerful generative models to iPhone, iPad, and Mac. Apple Intelligence is designed to protect your privacy at every step. To deliver this advanced security architecture, whenever possible, Apple Intelligence processes tasks locally on the device, but more sophisticated tasks require additional processing power. Private Cloud Compute, or PCC, allows us to scale our computational capacity and draw on even larger server-based models for these complex requests. These models run on servers we have especially created using Apple Silicon and offer the privacy and security of your iPhone from the Silicon On app. Private Cloud Compute is a great example of how we're investing in and adopting open source technologies. We draw from the security properties of the Swift programming language to run software with transparency built in and leverage the high performance and resilience of gRPC for the transportation layer. gRPC is a mature CNCF project with more than 8 years of upstream development. It is a widely known framework that can efficiently connect services across distributed infrastructure. And within Private Cloud Compute, we heavily leverage the building blocks of gRPC for the transportation layer. Bidirectional streaming is a core part of gRPC that we use to communicate load information between the PCC gateway and a single Apple Silicon server. Since privacy and security is at the root of our components, we ensure the response payloads are encrypted by the user device and routed using gRPC to the PCC gateway all the way to Apple Silicon machines. And finally, gRPC has a very robust liveness probing that is highly configurable. As gRPC controls its underlying transport, we lean into its resilience to ensure it is capable of performing these probes. From a technical standpoint, some of the libraries we use are gRPC Swift and Swift Protobuf, which in simple terms are the Swift implementation for gRPC and Protobuf. And at Apple, we've written all kinds of services in Swift, from iCloud Keychain to App Store processing pipelines and SharePlay file sharing. And when building out a service that supports Apple commitments to user privacy, Swift was a natural choice for several reasons. From a performance standpoint, Swift has a very low memory footprint that keeps the system resource usage down. This enables us to make the most efficient use of our hardware for inference within PCC. We're also able to leverage our existing investment in memory-safe protocol implementations. By using Swift libraries throughout the stack, we minimize the amount of unsafe code parsing untrusted data, shrinking our attack surface. The same policy was applied throughout the entire code base. And finally, we spent a number of years collaborating with the community to build an open-source Swift server ecosystem that has great solutions for privacy-oriented services. Private cloud compute is a great example of how we're bringing together two open source ecosystems and a decade of innovation. High resilience and performance of gRPC with the security properties of Swift enables us to bring industry-leading device security models into the cloud. We're looking forward to continue our investment in these communities and make Swift a platform for the cloud and server development. If you'd like to learn more about our use cases in the cloud-native space and how we engage with the wider ecosystem, you can attend one of the 10-hour talks delivered by Apple engineers at this conference. And to explore how Swift can be a fast, modern, and safe language for your server, you can check swift.org/server for more details. And if you'd like to learn more about private cloud compute, you can go to security.apple.com. This is Katie Gamanji, and I look forward to seeing how you can shape the open source ecosystem. Thank you, and enjoy the rest of the conference.